Okay, welcome back. We're going to continue with an R&D problem, a research development expenditure problem of a firm. So what you see here, first look at the red colors, okay? So in a continuous time framework, we're going to look at a firm problem. So this firm has this market value at the initial date, okay? So this, of course, depends on the discounted sum of profits, future profits, right? Now, there's this fixed interest rate, and we look at the profit. So the profit function here depends on production, obviously. So production function is NT to the theta, LT to the alpha. So N here is the technology variable. Okay, you may imagine that this is process innovation. So that would be quality of the production process or the productivity of the production process in general. Or you may imagine that this is the number of different products the firm sells in markets. Okay, so it is a product innovation or horizontal innovation. So P is some price level, which we take as fixed here for simplicity. And again, L is labor. The firm pays a cost for labor services, okay? Here, wages W. And then this is the R&D expenditure, okay? Because this is a knowledge variable, it's some sort of technology. So this technology, so the firm can invest into this technology by making some R&D expenditure, right? So here theta is some positive number, so there could be increasing returns with respect to N, but alpha is between 0 and 1, so the production function exhibits decreasing returns to scale with respect to labor, okay? So diminishing margin productivity of labor, basically, right? So obviously, we should talk about the R&D technology here. So if the firm directs RT units of cash to R&D, then there is this production function for new innovations, okay? Again, these innovations could be product innovations or process innovations. Doesn't really matter in such a simple problem. But obviously here, we also introduce decreasing returns in R&D technology, right? So this is basically the square root of RT. Then we also assume that there is some loss of technology in time, right? So you may imagine that if these are the products, the firm may lose some competitive firms. The intellectual property could be lost, or there is some sort of technological regress depending on other technological aspects of the society. So in time, new innovations in other sectors may make your technology obsolete in time, okay? But delta is not, I mean, delta could be 0, you can still solve this problem, okay? Now, clearly, you can write the Hamiltonian function very easily. So this is the current value Hamiltonian, as you see. So I write the profit plus the cost state variable Q times the constraint, right? Now look at the blue colors, okay? Follow the blue colors. I basically write the first of the conditions. So here I assume that firm will spend a positive amount of R&D. So we can also look at the corner solution, but here corner solution will not be optimum, as you see from this derivative, right? Then you have the labor. Again, I assume that firm will have a demand, a strictly positive demand for labor. So firm will produce. Otherwise, there's no product, and the story is not meaningful. Then we have the cost state equation, right? Q dot minus RQ. Then this must be equal to the derivative of the Hamiltonian with respect to N times minus 1. So this is just that derivative, right? So I look at the Hamiltonian, so I take the derivative with respect to N. So first I have theta p n to the theta minus 1 L to the alpha, and then I have minus q delta, right? And finally, obviously, we have the transversality condition, right? Now look at the green colors, okay? The first two equations allow us to write R and L as functions of Q and N, okay? Because in this problem, we're gonna at the end arrive at a dynamical system of Q, the co-state variable, and N, the state variable, which is very similar what we have done for the optimal growth model, right? So these are the optimal levels depending on Q and N. The rest is constant, right? So then we can substitute these things in the co-state equation. So this is your co-state equation again. So you can replace L, right, in your co-state equation. This is L to the alpha, right, this part. Then you write the co-state equation this way. Now be careful here. Now co-state equation, of course, depends on N, your state variable, some constants here, right, depending on wage and price, and some technology parameters, and also the discounting term here, right? So now we have R, and also we have delta, because delta we are paying for such a knowledge depreciation, right? So look at this equation. So this equation is a linear first order differential equation in Q, all right? So this equation right here, let me annotate. So this equation right here is a first order, right? It only features the first order derivative with respect to Q. It's a first order linear differential equation because this term is linear in Q, right? And then there is this term. This term is now changing in time, but it doesn't really a big deal. The question is this. So what will happen to the co-state variable? Now, in some papers, you will see that the author will leave that equation as it is and create a dynamical system. In some other papers, which are more meaningful in my understanding, you're going to see that this differential equation is an unstable differential equation, right? Because if you draw this, phase diagram for QT, you have something like this, okay? And of course, that depends on N, right? That depends on NT. So when NT changes, that location will change, but essentially the slope is always equal to R plus delta and positive, right? What does it mean? It means this differential equation is unstable. Okay. Now, what happens when this differential equation is unstable? Well, either QT goes to positive infinity, right? Or QT goes to 0. All right. Now, some authors, when some endogenous growth theorists, for instance, you can see a lot of such stuff in Pietro Paretto's work. They just assume that since this equation is unstable, this must be true. Okay. In other words, the firm will choose QT in such a way that Q dot equal to 0. All right. Now, if you look at this equation in this particular way, what does it mean? It means the firm will always equate Q by looking at this equation. Okay. So here I denote this part as Z. Okay. Z function, just for notation. And then there is this part that depends on NT, right? So firm at the initial date t equals 0, at this initial date, okay, the firm will choose QT always as a function of NT. So you may write this function as let's say C function, and it always depends on N. All right. And that function could be convex or concave, depending on this, right? Depending on whether this is greater than 1 or less than 1. All right. Now that's on the hand. On the other side, from the for the state variable, we have this equation, right? This one. Now what do I know? I know exactly that R is equal to this, right? RT is equal to this at the optimal point. So if you put this into that, you will find this differential equation. All right. Now this differential equation will give you the n dot equals 0 locus. Okay. And as you see, it is linear, right? Now what do I have here? First, this is n dot equals 0 curve. And this is basically q dot equals 0 curve, right? Now, depending on the shape, again, that could be that as well. Or if theta divided by 1 minus alpha, if this is just equal to 1, so if theta is 2 times 1 minus alpha, it is linear. But this is a singularity condition, so we don't believe that theta and alpha are related in this way. So in general, either it is greater than 1 or less than 1, right? So either it is convex or concave. But if it is just concave, there is just one steady state here. If it is just convex, there is again some steady state somewhere here, right? Now question becomes, what are the dynamics here? So you have n dot equals what was it? So it is problems with this whiteboard. So it is 2 gamma squared q minus delta n. So it is 2 gamma squared qt minus delta nt, and you have q dot equals r plus rho qt minus some function of constants times nt to the theta 1 minus alpha minus 1. Okay? And you have n0 given. Okay? So what you can do, of course, is to find the steady state, and the positive steady state is there, q star n star, right? Finding that steady state and then linearizing this, because this is nonlinear, right? So this part makes this model nonlinear. Then linearizing the model, you can tell me, you can find the linearized version. Okay, q dot t. So you can find nt dot qt dot equals some matrix times nt qt plus some vector. Okay, then you can tell me by looking at the determinant of A and the trace of A, so that this particular steady state is what? Okay, and you must be just telling me that, of course, it looks like a lot of, it looks pretty much a settled path, but it is up to you. The rest of the problem, so you should find the linearized version, first the steady state, then the linearized version, then eigenvalues, then you can tell me what type of equilibrium is this. All right. So let me now stop for a moment for questions or comments or other stuff. Anything? Good. This just proves that I am the perfect teacher. So if you have nothing further, let's look at this fishery problem. So let me again share my screen. Okay, so all right. So now in a fishery problem, what we are going to do is this. Again, there is a firm. This firm is now a fishing farm. Again, we have the value depending on some market interest rate, right? Let's say RT. And profit. So let's imagine the profits. How we can define the profit. So if price of the fish is P, and if ET is the extraction, all right, then that will be my sales. Okay. Now suppose that there is also this cost, and the cost will be perhaps increasing. So this is kappa. So suppose that cost is increasing in this way. All right. So it's a convex cost function. And that's it, right? You may also put some fixed cost, but it's not really essential. All right. So again, P is the price, ET is the extraction, the number of or the amount of fish you extract at instant T. All right. And this part is the total cost of extracting ET units of fish. Okay. All right. So kappa is positive and P is positive. So these are given. All right. Now the number of or the amount of fish is going to have this law of motion. So first, if you let them behave as they are, so they have what? They have a death rate, okay, and a birth rate, okay. Let's say the birth rate is beta, and then there's this birth function ET, sorry, NT, I'm sorry. All right. And minus, obviously, if you extract ET, other than that, you also remove a certain amount of fish from the fishing farm. All right. So here, the death rate will be that, beta will be positive, and you have the extraction. All right. Now, what is the problem? So problem would be now, once again, you have the initial stock given, right? So the problem is now a Hamiltonian problem, obviously, right? So you have the instantaneous reward, okay, plus you have the constraint. So constraint is that. Okay, so there is regeneration, there is death, and there is your extraction. All right. So how you can tackle this problem? Well, you're going to look at so your control variable here is ET, right? Your state is NT and your cost state is QT, right? So with respect to ET, you have what? You have the derivative, so P minus kappa ET, all right? This is that part, plus QT minus 1, right? So the derivative of the Hamiltonian with respect to ET is just that. So if you look at this equation, you're going to see that price must be equal to the cost. Now, cost has two components. One is that, the other is that, right? One is concerning the marginal cost of extraction. The other is extracting the fish today, right? The cost of extracting the fish today, because that leaves a lower amount of fish for tomorrow, all right? So then you have your state equation. State equation is just here. So let me just say that this is your state, right? Then you have the cost state. Cost state is what? Q dot T minus RQT. So this will be equal to the derivative of the Hamiltonian with respect to NT times minus 1. So it will be what? There's no N here in the reward. So you have minus QT, now the derivative with respect to N. So you have minus delta plus beta F prime NT. Okay, so you have that. Then you have the transversality condition. Transversality condition is again limit QT e to the minus RT NT equals 0. All right. So let me use this side with a different color. So again, I have one condition that tells me this. Okay. Then I have another condition that tells me Q dot T divided by QT will be equal to R plus beta, R plus delta, okay, minus beta F prime NT. Beta F prime NT. Okay. Then you have the state equation. Now, again, what you do is replacing using this equation, you can replace ET in this way. So it is P minus QT divided by kappa, right? So if you put this into that equation, you're going to find N dot T equals delta NT plus beta FNT minus P minus QT divided by kappa. Okay, so in other words, NT dot is this differential equation. Again, NT and QT. Then you have this equation, this one, right? And that's also a differential equation that you can write in this way. Theta NT QT. Then again, you have the initial value and you have the dynamical system. Similarly, once again, this differential equation is unstable. So you can just directly tell me that the firm chooses QT to make Q dot T equals 0 in the initial point and for anything. Okay. So this is the jump. This is the jump. So in some papers, you're gonna see this term, jump. So the variable jumps. So here that jump is because this differential equation is unstable an unstable differential equation will take the firm either to Q positive infinity, Q equals positive infinity, or Q equals 0. Both of these are not very meaningful. One is, again, violating the feasibility, another is violating the transversality. So then the firm will make Qt jump exactly to a value Q star that makes Q dot equals 0. All right. Again, you're gonna, if I give you f function, if I give you the function f here, the birth function, then you can write your dynamical system, find the steady state, then linearize it around that steady state. Then you can tell me what type of equilibrium is this. Okay, this part is essentially that's the part you should understand, right? The cost has a static component and a dynamic component. Okay, and marginal cost. So this is now the marginal cost, and this is the marginal return. Okay, so that's the fishery problem. Any questions? Okay. If you are all happy with the content, I'm going to show you one final example for today. So how much time we have? We started 55. We have about 10 minutes, I guess. Okay. So let me now show you another example. So here, this is directly from your textbook, by the way, Takayama. An example with a finite horizon. Okay. When I say finite horizon, I basically mean the consumer will die at some point. Okay. So here there will be some utility. So this is a lifetime saving problem. Okay, or lifetime wealth accumulation problem. All right. So this is typical utility stream from consumption, but again, t is less than positive infinity. All right, that's important. The problem is one of finite horizon, and that particular decision maker will benefit from leaving some bequest to her offspring, to her kid. All right. So let me just make sure whether I wrote this correct. Yeah, there's one problem there. So this will be obviously T. Okay. Now let me again specify what we have here. So we have the consumption of the person himself or herself. So this is typical. The only difference is that T is now a fixed number. Okay, so there's a certain end point of life. Then A here is the asset stock. All right, so there is this asset stock. That asset stock follows this time path. Okay, and you may actually add some income source as well. Okay, suppose that gamma is positive. Okay, you may imagine that this is a transfer or this is some sort of wage income. All right, now what happens? This consumer has some bequest motive, right? Because at T, she's gonna leave this world. At that date, she will have some sort of asset, all right? And leaving that asset will give utility, okay, to this agent. So we assume psi, the derivative of psi is positive. Okay, so there is a bequest motive. Okay, and as is typical, initially this is positive. Okay, and R is also positive. All right, so that's the problem. Now you see it's a bit strange because the state variable at a particular date will enter your problem in this way. Okay, and of course the consumer looks at the present value of it. Okay, not the current value. That's the current value. Current value of what? Current value of utility originating from the bequest. Okay, but consumer cares about the present value, right? Because she'll be taking that decision at t equals 0. And there's, of course, consumption here as the control variable. All right. So how do we tackle this problem? So most of the stuff will be the same. All right. Most of the stuff that we're going to do is the same, but we're going to be careful with one thing. First, we're going to use present value Hamiltonian. Because it is much more intuitive for such problem, for a problem like this. Okay. And then in the second case, we're going to shut down the bequest motive. Okay, so we're gonna put a constraint like this. So tell the consumer will tell us, okay, I don't care about my kid. At the end of the day, when I'm leaving this world, I should leave no bequest, no asset stock for future, right? Because my life is ending. Optimally, I should be consuming all of these assets. I should eat up. All right. So these are the differences. But first, we're going to look at the version with a bequest motive. Right. So as I said, most of the stuff will be similar to what we have done, but we're going to look at the present value Hamiltonian. All right. Then I have PT, right? And my constraint is what? RAT minus CT minus plus some gamma. Gamma is exogenous and fixed. All right. So once again, I have the control variable. So the derivative of the Hamiltonian with respect to control variable should be 0. Let's assume that CT is positive. All right. Then we have the constraint itself, right? RAT minus CT plus gamma. Then we have the cos state equation. Now be careful. Here I write the cos state directly in this way. Right, so it is minus PR. Okay, and the transversality is what? How do you not write now transversality? Now, if this was an infinite horizon problem, you would write something like this. You would write limit PT AT equals 0 when t goes to positive infinity. Now t goes to t, which is less than positive infinity. So how do you write it? Well, don't forget, you have a particular term in your you have this particular term, remember. So it tells you something about the value you should be attaching to this variable. You may imagine that this variable itself, so you may actually imagine AT is like a control now, control variable. Right? Because it has a return. Right? What's the return? You can write the return in this way. Right? That's the return. Now, this must be equal to what? Are you there? This must be equal to what? My friends, it's very simple. Are you there? So if this is the return of holding a particular amount of this asset, AT, what is the cost in present value terms?
0.
No, it cannot be 0. If it is 0, then I would hold an infinite amount of it.
But we said that AT equals to 0.
No, not here. So it will be the other version. Here, the consumer has the bequest motive. This derivative is positive. Okay, we have less than a minute. So it is 2:35. Think about this during the break. It's very simple because if this is the return, there must be a cost. And what is the cost of holding the asset? Let's meet at 2:50. All right. Let's meet at 2:50 because it's about the stop.
Okay.
All right. Think about this during the break.